Okay, calculus students, a quick rundown of the notes from today. Today was the final of the prerequisite sections that we are doing in this little prerequisite chapter, and today's discussion is all about functions. Okay, our objective for the day is to regain an understanding of functions and their properties. The way we're going to do that is we're going to be able to demonstrate the ability to evaluate provided functions, determine the domains and ranges for those functions, apply the vertical line test, and interpret transformations to those functions. The essential question, which you should have an answer to by the time you have completed the last of the assignment questions, is have I mastered the concepts and workings of functions and tests for functions? Okay, once we examine an equation or a graph and determine that it is a function, we have a new notation called functional notation. Okay, so here we have any function, happens to be a linear equation rather, and once we look at an equation and determine that for any x value that gets plugged into this equation, that no one x value can possibly yield more than one y value in return. For each x, there is only one y. Once we have determined that, we no longer write y equals 2x plus 1, we write f of x equals 2x plus 1. Seems like a very slight thing to do, and people may question whether or not it's really that important. Okay, it's just one of those things that is done, so now you know what it actually means when you see it. It is read f of x equals 2x plus 1. Okay, and of course f is not the only name that could be used. It could be g of x, h of x, k of x, things like that. So it can be replaced with any variable or symbol without changing the fact that this is a function. Okay, now there's a special way they ask us to look for functions at particular locations. So instead of writing out something in verbal or written form, what is y when x is 3, we actually have a very condensed notation that asks the same question. So we've already talked about functional notation, f of x equals 2x plus 1, but let's say we are interested in knowing what's going on in the domain at 3. Okay, well, the notation of that is to basically replace every x that you have in the equation with the value that you want to evaluate at, in this case, a 3. And of course, what you can see there is that when you replace those x's with 3's, now the entire right side of the problem becomes numerical and it can be simplified. So this is pronounced f of 3. And it means what is the value of the function when x is 3. And in this case, f of 3 is 7. 2 times 3 plus 1. Okay, now everybody's favorite topics from once upon a time, domain and range. Of course, domain is all of the possible x values that a graph has to offer, and range is all of the possible y values that a graph has to offer. Okay, and we can get a lot of information from the graph if we are provided one. We have the difference between an open dot and a closed dot. A closed dot in a graph means that that particular location in the graph is not only a boundary to an interval, but it's also included as part of the solution to the graph. Whereas an open dot in a graph means, once again, it is a boundary to an interval, but that location is not included as part of the solution for the graph. Okay, when we're answering questions about domain and range, there's a lot of different notations that do show up. Square brackets is one of those. Okay, when we announce an interval to a domain or range and we use the square brackets, that is a closed situation, meaning we are announcing the end of the interval, and that end is also included as part of the interval. However, when you see the curved parentheses, okay, we are again announcing the end of an interval. However, this end of the interval is not included as part of the interval, so we are talking about an open interval. Okay, if infinity is part of the solution set, if we have a graph that has legs that run off to positive infinity or negative infinity, okay, infinity always gets parentheses because infinity is always treated as an open location, basically because we cannot go to that particular location on the number line and point at infinity and say, here it is. If your answer to a question or response to a question is a collection of locations, we use curly braces to list off the values. Now, curly braces are used for set notation, and set notation is used for when we have an answer and our answer is that there is more than one answer. So in this particular case with domain and range, a lot of times we have curly braces when we're just going to have some a series of specific values, but not the space in between those values. So those numbers are listed off and delineated by commas in between them. Okay, values in curly braces are always considered to be closed since they obviously must exist in the graph in order to be considered for a domain or a range response in the first place. Okay, so when you're checking to see if you have a function, okay, well, the straightforward definition is that for every x that you have, you can only have one y. Okay, but if you do have a graph to go along with this location or this equation or function, okay, the vertical line test is a very easy way to go about testing for a function. Vertical line test basically says if there are no vertical line or there is no vertical line that can intersect a graph at more than one place, then the graph is in fact a function. And we looked at several examples there. The one on the left, the red linear equation, is absolutely a function. No vertical line anywhere positioned along that line can intersect this graph more than once. The purple one, which looks like some sort of a distorted and rotated cubic function, is absolutely not a function. Okay, just about any vertical line that we put in that graph is going to hit this graph 3 times, and it's not allowed to hit more than once. Okay, the sine wave there in the green one, that one is a function. No one vertical line hits it more than once. Then we have a parabola, a vertical parabola, upwards opening. Okay, that one is a function as well. Okay, we have some type of a absolute value graph going on in the brown one, not a function. Vertical line will hit it more than once. And then we have a leftward opening parabola, and once again, that one is going to fail the vertical line test. Okay, so we just saw how those work. Okay, now transformations to functions, this is probably where we get into the biggest piece of information here. Considering the generic parent function y equals f of x. Now remember, f of x is just any function, so it does not matter what this graph is or what it is doing. All that matters is it is a function that exists in a graph, and all functions will obey the following transformations. Okay, any function can be translated upward by simply adding a constant to the end of the expression. So essentially we are increasing the overall value of y, and increasing the overall value of y is just going to shift the graph upward. Similarly, it can be translated down by decreasing the overall value of y. Now, it can be translated leftward or rightward by directly affecting the x value, but please remember, when these values get inside of there and directly affect the independent axis, the signs operate in the opposite direction that common sense would tell us that they're going to operate. So to translate left, okay, leftward is where the negative numbers are, but it's actually going to show up as a positive in that equation, and vice versa. To translate right, well, rightward is where the positive numbers are, but this is going to show up as a negative number inside of that format. Okay, our graphs can be reflected over the various axes. Okay, if we want to reflect over the x-axis, basically what we are doing is we are keeping the x, but changing the sign of y. So what we want to do is we want to basically change the sign of everything that y equals. So we're going to change the sign out in front of the function and make that negative affect all of the signs of the function. To reflect over the y-axis, the y value is going to stay the same, but the x is going to be changed. So we're going to get inside of the parentheses this time and directly affect the sign of the independent variable. We also could face a rotation around the origin, and hopefully, as you remember, okay, that's going to cause sign changes everywhere. So we need to directly affect the sign of y and directly affect the sign of the x simultaneously, and that will cause a rotation around the origin. Okay, so that's basically the information that we looked at in a nutshell. We did have some time in class to work on this assignment, but it was not really enough time. So we will continue this this exercise in class on Wednesday. Okay, that will conclude the prerequisite unit. So Thursday will be a review day where we'll have some practice problems on that. And then Friday will be our first test of the year, encompassing all of the prerequisite topics. So begin preparing yourselves for that.